Hello class, this is Dr. Uzuchukwu with your final lecture, lecture 9, and we're going to dive right into inferential statistics. Alright, so inferential statistics allows us to generalize from a simple random sample to the population. Now we've done this already with chi-squared, where we were using contingency tables which allow us to look at categorical variables, right? The nominal or ordinal variables, and you can look at that with the contingency tables or crosstabs. So inferential statistics, though, can also be viewed in terms of confidence intervals, which we'll learn about in this class, and hypothesis testing, which is what we already did with chi-squared. We're just going to do it again here with regressions. Alright, so hypothesis testing allows us to determine whether a relationship between the independent variable and the dependent variable exists in the population. We essentially want to be able to reject the null hypothesis that there is no relationship between these two variables in the population. And then we've got our confidence interval, which is going to be new for you, a new concept in this lecture. And it allows us to take our regression coefficient to a whole new level, folks. So here we're able to not just use the regression coefficient to understand what's going on in the sample, but the confidence interval allows us to see what's going on in the population. It gives us a range of what that regression coefficient would be in the population. So we're going to dive deeper into that. Be sure to read the bullet points here because I'm not necessarily reading through them for you. Okay? So Ttest decision rules. Most of our decision rules are based off of the 95% confidence level. Some software you're able to manipulate it and maybe do 90 or maybe do 97, but for this class we're strictly sticking to the 95% confidence interval. Okay, and so we've got a few decision rules when we're talking about the t-test and the regression. Decision rule 1, if B1, which we know is our regression coefficient, so if B1 is within two standard errors of 0, we are unable to confidently conclude that that parameter, population parameter, beta 1, is either not a negative or positive. So therefore, we tentatively accept the null hypothesis that in the population there is no relationship between the two variables. So let's take a look at this graphic here, this graph here, that allows us to understand what I just said a little better. So we see in the no-fly zone, I like to call it the no-fly zone because that allows people to understand, what's really happening here. Anything between that -2 and +2 is in our no-fly zone. In our no-fly zone, we have to tentatively accept the null hypothesis. Why? Because it's possible that it could be 0. It could hit that 0 marker, which means that there is no relationship. Okay, so granted it could be 1.7, but because it's in that no-fly zone, there's a possibility that it could be 0. And 0 means no relationship. Okay, so moving on, B1, if B1 is more than 2 standard errors above 0, okay, so that means it's either, between that -3 and -2, or between that +2 and +3. Above 0. So that's the +2 and +3. We confidently conclude that the population parameter is positive because it's above 2 standard errors, right? So it's above +2. So the relationship between the independent variable and the dependent variable is positive. Okay, And then finally, if the B1 is more than 2 standard errors below 0, meaning that it's in the negative range, right? Then we can confidently conclude that that relationship between the dependent and independent variable, that relationship is a negative one. So as one thing goes up, the other goes down, right? Statistic. All right, so in your regression output, you'll see it as T, or you'll see it as Tstat. And the regression output indicates how many estimated standard errors the sample regression is from 0. So I said this in the previous slide. I talked about it in terms of B1, right, and in terms of standard error, but this is what it looks like in terms of calculating it. So so that you understand where the T is coming from, you can see that it is your regression coefficient, B, whatever it is, B1, B2, and so on. Your regression coefficient divided by the standard error, which you find right next to that that regression coefficient column. It's to the right, directly to the right of that column. So dividing the sample regression coefficient by the estimated standard error, that is how you get your T statistic. Okay, it's really just that simple, but we don't calculate it. I mean, you can obviously, but the regression output just provides that information for you. But it allows you to see through this calculation what that T is really telling us. So let's take a look at the output. Okay, so we've got a bivariate regression here because we only have one independent variable that we're looking at to assess its relationship with the only dependent variable that we have here. So 2 variables, bivariate. All right, and we've got our B1, the 4622.9, right? That's our B1, and we divide it by the standard error, 199.7. And we get our T statistic, 23.2. That's it. That's really it. So the T statistic means that the sample regression coefficient is $4,623. Excuse me, sample regression coefficient of $4,600 is 23 estimated standard errors away from 0. Recall that we wanted to all we needed was 2, right? We just wanted to be above 2, positive 2, or below negative 2, right? In order to be not in that no-fly zone, and to be in the fly as much as you want zone, okay? But right now it's telling us that we are 23 standard errors away from 0. So, like I just said, recalling our decision rule, we can actually, I just copy pasted from the previous couple slides. I just copy and pasted that decision rule, and it's really just that straightforward. You see our T of 23, and the decision rule says that if it's more than 2 standard errors above 0, in this case it's 23, then we conclude that there's a positive relationship, not just in the sample, but also in the population, because we're able to reject the null hypothesis. Okay? All right. So, taking another example using another bivariate regression output, we've got gender against salary. So our regression coefficient, or our B1, is 12,776. We've seen that number before in previous lectures, divided by our standard error, 1046, and we should get the T that we see when you keep going, looking down that table. You should see 12.2. So the calculation gives us just that. So that 12.2, what is it telling us? It's telling us the same thing as it told us before with the 23, right? In this case, it's telling us that the sample regression of $12,777 is 12 estimated standard errors above 0. So again, we go to our decision rule, and we know how to conclude here. We know that we not only can generalize to the population what we're seeing here in the sample, but that what we are seeing here in the sample is that there is a positive relationship between gender and salary, specifically that men, right, make about that much more than females, about 13,000 more than females, at least in the sample. Okay. All right, so let's look at a multivariate regression and talk about our T-stat. So we've got two variables here, gender and education. In terms of their T-stat, we see that for gender it's 7.63, for education it's 20.35, and they're both well above 2 standard errors. So what can we conclude? In the population from which this sample was drawn, men make more than comparably educated women. Said another way, in this population from which the sample was drawn, men have higher mean salaries than women, holding education constant. Okay? So what's our second conclusion? I'm going to give you a second to think through it. Okay, so our second conclusion that we're able to make is also that in the population from which the sample was drawn, the more educated workers earn more than less educated workers of the same sex in the population. I said the population twice, but just to, emphasize that. In the population, each additional year of education increases expected salary, holding gender constant. It's not too bad, right? We are getting it. It's coming together. Okay, so another multivariate. This one's got a lot more variables in it. We've got a set of dummies for race. We've got two interval level variables, education and federal service, and we've got another dummy variable, gender. Okay, and our dependent variable is still salary. So remember that the reference group for this set of dummy, because we don't see it here, has to be white, because we don't see it here. So everything that we see here is being compared to the white employees in this sample. So, but what can we conclude about Asian employees based on what we now know from the T statistic? We're only looking at that T statistic column. So what would you say that we can conclude? We haven't done this particular one yet, so I'm going to give you a second to think about it. It's, first of all, when we use our decision rule, we have to think, is this greater than 2 or less than 2? As in, is this in that no-fly zone or outside of the no-fly zone, where you can fly all you want to and reject the null hypothesis? So yes, it is below 2, or it's within that no-fly zone. So we have to tentatively accept the null hypothesis that in the population, there is no relationship between the two variables. Now, in the sample, right, we can see that Asians make about $632 more than whites, because we can see the 632 for the B1, right, for the regression coefficient. So we know that this is telling us that Asians are making more than whites when we hold gender constant, education constant, and years of federal service constant. Okay? We have to remember to hold those things constant because this is a multivariate regression. So never forget to do that, particularly for your quizzes, because you're gonna get mad at yourself. Can't be mad at me because I've told you before already. So remember holding those things constant. Asians make about $632 more than whites in this sample alone, right? In another sample, it may look differently, but in the population, This T statistic is telling us that there actually is no difference. There's no difference. It's no difference in salaries. Interesting, right? For black employees, let's take a look at that. What is that telling us? Our T statistic, we should all agree on, is negative 3.728. And notice here, notice with all of your T statistics and and regression coefficients, that if it's negative for one, it's negative for the other. If it's positive in one area, it's also positive in the other. It just come together. They're the same, direction. They're the same positive or negative direction. So you're not going to get a positive regression coefficient and then see T as a negative. It just won't happen unless someone jotted it down wrong. But your computer will never provide you that type of difference in information. Okay, so getting back to the question here, what can we conclude about black employees? Well, the first thing we go to, right, is that column, and we look for the T statistic for the black variable, and it's negative 3.728. The second thing we do is we think, okay, is this number in the fly zone or the no-fly zone? Well, I believe it's in the fly zone. We can fly all you want zone. And so we can reject the null hypothesis and say that there is a relationship or there is a difference, I guess, in mean salary between blacks and whites in the population, right? That there is a relationship, and that relationship is negative. We know that it's negative because we see it not just in the regression coefficient, but we see it with the T, and we see that this is a negative relationship. Specifically, that black employees have lower salaries than white employees, holding these other variables in this model constant. Okay? That's what we're going to see. All right, so now that we've talked about the T statistic and we are so comfortable and so understanding how to interpret the T statistic, let's move on over to the p-value. The p-value, recall from the chi-square test that it is the probability of error. Okay, and the p-value of 0.05 means that we have a 5% probability of error. If we see something like 0.7, then that is a whole lot of error, folks, and we don't even want to mess with it. About 70% probability of error at 0.7 p-value. Okay, so for the relationship between education and salary here, again, is this a multivariate or a bivariate regression output? Bivariate, right? And it's a regression of salary on education, and we can see that the p-value here is 0.000. I'm sure it can probably go down a few before we actually get to any numbers. We can never really say 100%. So while you see this as 0.000, a lot of times if you actually do the calculation, you will find that maybe 19 zeros down that there are some actual non-zero numbers, 1, 3, 7, and so on. So we never ever say 100% confidence for really anything ever. But when we see that 0.000, we know that we can at least be 95% confident. Okay, and 99, honestly. So this p-value is telling us that there is a very low probability of type 1 error. So take a look at our chi-square lecture where we talked about the different types of error, and type 1 error is essentially incorrectly rejecting the null hypothesis. Okay, and so so that one we know how to control to measure type 1 error. Type 2 error is a little more difficult, and we talked about that in that previous lecture, but at least we know the probability of making a type 1 error. So therefore, we reject the null hypothesis and conclude with at least 95% confidence that in the population, expected salary rises with education. Okay? We don't have to hold anything constant because there's nothing else there to hold constant. This is a bivariate regression. All right, so another regression, I call it bivariate. Of course, we have learned it to be multivariate because it's a set of dummy variables. And the one variable that we're looking at here is race. So for the relationship between Asian and white and salary, the p-value is 0.130. And that should tell us what again? So the p-value is telling us that there's 13% error here. 13% chance of a type 1 error, a 13% chance of incorrectly rejecting the null hypothesis, incorrectly saying that there is a relationship when there really isn't. That's what that means. When there really isn't a relationship and we're saying, yep, there is a relationship. So because we are only willing to accept up to 5% probability of error, we therefore tentatively, we can never fully accept anything, so we tentatively accept the null hypothesis and conclude that in the population there might be no relationship or there might be no difference at all between the mean salary for Asians and the mean salary for Caucasians. Okay? So, what you should notice from this slide and the slide where we talked about this very same output and we looked at it from the t-value perspective, we can see that the conclusions of t-statistic and p-value are consistent across the board. So here we're seeing a p-value of 13% error. And then we go to our t of negative 1.5. We should see immediately that that is in the no-fly zone, immediately. So being that it's in the no-fly zone, we have to tentatively accept the null hypothesis, okay? So let's take a look at another one. We've got 0.008 for Hispanics. Then we've got negative 2.677, right? That's telling us that it is above, it is outside of that no-fly zone, right? And so we can reject the null hypothesis and fly all we want to and talk about the relationship that exists in the population. Okay, so sample statistics versus population parameters. Sample statistics, we talk about it in terms of regression coefficients. That is a sample statistic. Beta weight is also a sample statistic. It was very similar, if you remember, to a correlation coefficient, sample statistics. Their interpretations should always include the words in the population. Excuse me, I'm getting carried away here. In the sample. Population parameters are such as hypothesis tests, confidence intervals, so t-statistics, the p-values, the population parameters. These are all, or beta, these are all population parameters. Hypothesis tests and confidence intervals help us to understand whether the statistic or the findings from a particular sample can be generalized to the population. All we've been talking about so far, a lot of what we talk about is what's going on in the sample. What's going on in the sample? What's happening in the sample? And so statistics, the purpose of statistics is to understand, use a small sample, a big sample, a sample nonetheless, to understand what's happening in the population, right? Because a lot of times we cannot sample an entire population. We cannot go and survey the billions of people in the globe, right? But we can look at the city of Baltimore, or we can look at the a subset of the residents in Baltimore, and it may help us understand Baltimore in general. We may look at the statistics class for Dr. Uzuchukwu, and it may help us understand other statistics classes in the state of Maryland, something like that, right? And so statistics and samples helps us tremendously to save money and to save time and to make things actually doable, because a lot of times we can't reach an entire population. Okay, so anything that has t-statistics, that we're talking about t-statistics or p-values or confidence intervals, we always use in our interpretation the words in the population. Okay? Hypothesis tests. So the t-statistic is a ratio. We've talked about how we calculate it with the sample regression coefficient and the estimated error. Anything that increases the absolute value of the sample regression coefficient, right, or shrinks the estimated standard error will cause the t-statistic to get larger. So I would challenge you to just pull out two numbers, increase one, decrease the other, and watch how that number and watch what that number does, right? What the t-statistic becomes. That's essentially what the first line is saying. So if your regression coefficient increases, your t value will also increase. Okay? If your estimated error decreases, your t value will also increase. Okay? But if your estimated error, if you have a much larger error, guess what's going to happen to your t-statistic? It's going to get smaller. And so when you have a whole lot of error, you're not going to be able to generalize to the population because your t-statistic is getting smaller, and it may actually get so small that it falls into the no-fly zone, right? Between 0 and 2. Yeah? So the larger your sample size, the smaller the standard error will tend to be. So a lot of times we try to get a very large sample size, or a large enough, I say very large, but a large enough sample size that is representative, allows us to really understand the population. And when we have a large sample size, it sort of kind of gets rid of these errors that might occur in statistical calculations. So the larger your sample size, the smaller your standard error. So the goal is always to get us a large enough sample size. Also, if your sample size is large, you are likely to find that at least one of your relationships is statistically significant, and they may all be statistically significant. You may find that, and even though it's statistically significant, it may show that significance means that there is no relationship. I'm going to say that again. So you may see a t-statistic of 2.5, right? So that tells us that it's in the fly all you want zone, meaning that we reject the null hypothesis and we say that what we're seeing in this sample exists in the population. Then we go over to what we're seeing in the sample, and we're seeing that there is no relationship. We're seeing that, for example, blacks and whites have similar income. So that regression coefficient may say something like 1, or something small enough to be so close to each other that there's no difference. So just because something is statistically significant doesn't mean that there's a very strong relationship. It just means that this statistics is allowing us to see, to confirm from this sample what we might see in the population. Okay? Intervals, fun stuff. All right, so this is the last concept we're going to learn, and then you'll be on your way and feel so confident to complete your assignment 2 and to go into the workforce understanding and even applying all that you've learned in this course. So with confidence intervals, it is the population regression coefficient. We already know what the regression coefficient means. We are pros at that. We are completely familiar with that now. And so our confidence interval just allows us to see not just what's happening in the sample, but this is the population regression coefficient. So the sample tells us, the sample regression coefficient, right, tells us about what's happening in the sample. As the independent variable increases by 1 unit, whatever that unit is, right? the dependent variable increases by whatever that regression coefficient is. That's just how we interpret our regression coefficients. So in the for the population regression coefficient, that confidence interval is just telling us that in the population, as you know, the independent variable increases by 1 unit, that dependent variable increases by that range, that lower and upper confidence interval range that you see there in the output. So let's take a look. So we've got two variables here that's being regressed on salary. The two variables are gender and education. So let's look at the sample regression coefficient. We conclude that in this particular sample, folks, in this sample, men make $7,000 more than females, right? Men make $7,154 more than females, holding education constant. Okay, and then we move over to the population, go all the way down to the lower and upper bound for the 95% confidence interval, and we can see that the lower bound is 5,000, the upper bound is about 9,200, and so it's telling us that in the population from which the sample is drawn, men make about $5,000 to $9,000 more than women, holding education constant. So in another sample, that particular regression coefficient may be 9,000, it may be 7,200, it may be even as low as 5,000, but from all the samples, it's going to be in that range. It's going to be in that range, just depending on, you may get a sample that has a lot more executive women or something like that, but generally speaking, right, it's telling us what's happening in the population is going to be in this range between 5,000 and 9,000. Hope this is really making sense to you guys. So moving along with confidence intervals, what can we conclude about the relationship between education and salary in the population? I'm sorry, in the sample. So in the sample, what is the number we're looking at? We should be at 4648. So that should tell us, right, that in this particular sample, one additional year of education increases expected salary by $4,648, holding gender constant. Okay? In the population, as we scoot on down to the very last couple columns there, we see a range that is, it's pretty narrow, but, so that's telling us that this is pretty significant. So it's telling us that in the population from which the sample was drawn, one additional year of education actually increases expected salary anywhere between $4,178 and $5,117, holding gender constant. Okay? So here's that lovely chart again, or graphic again, and our decision rules. So recalling from slide 5, if it was slide 5, I'm not sure, we are between -2 and positive. If we are between -2 and +2, then we tentatively accept the null hypothesis. If we are greater than +2 or less than -2, then we reject the null hypothesis. Okay? And so here's an output that we're looking at. Should be the same from the previous slide. For confidence intervals, a similar decision rule applies. So first off, let's not forget what we just learned about confidence intervals. It's the population regression coefficient. So all the way to the left, we've got our sample regression coefficient. All the way to the right, we've got a range for our population regression coefficient. Okay, so that's one thing that the confidence interval does. The second thing that it does is allows us to generalize to the population. Okay, just like the other decision rules for T, statistic, and p-value. So if the confidence interval contains 0, then let's go right back to what we're talking about with the no-fly zone. Okay, if it contains 0, then we tentatively accept the null hypothesis. There is no relationship in the population. So for example, if the lower range is negative 3,000 and if the upper range is positive 4,102, just some arbitrary numbers I threw out there for you guys, we can see that the range goes from a negative, passes through 0, over to the positive. Okay, or we can see that it goes from the positive, passes through 0, still passing through that no-fly zone, and goes over to negative 3,000. That contains 0. So we have to tentatively accept the null, and we have to say just because it contains 0, there's a possibility that there is 0 relationship. There is no relationship. Okay, so if the confidence interval does not contain 0, of course, it is in that fly all you want to zone. Reject the null hypothesis, and then you can state that there is a relationship in this population, and specifically that relationship is going to be within that range, right? If the lower bound is negative 3,000 and the upper bound is negative 2,100, boom, there you have it, right? That's where in the population you could expect that relationship to hover around, okay? Or positive 3,000 to positive 4,100. Whatever it is that is not within that no-fly zone, that's where we're expecting the relationship to be. The fact that in the first bullet point we've got it crossing over 0 is telling us that we don't want to chance it, because there's a possibility that it may not be in these extreme ends of negative 3,000 and negative 4,000, that it may actually fall right there in that range of 0. So yet again, we've got an important notice up here that the conclusions, I said before, the t-statistic and p-value results are always consistent, always consistent. Okay, so I just want to add another consistent result to it, and that's the confidence interval. So if your t-statistic says one thing, your p-value will tell you the exact same thing, and your confidence interval should only corroborate that same story. Okay, so we're not going to reject based on our t and then accept based on our p-value and then reject again based on our confidence interval. No, we're going to reject for all three. They should all say the same thing, or we're going to tentatively accept for all three, because they should all tell us the exact same thing. Okay, so whenever a 95% confidence interval contains 0, I've said this before, but I think it's important in the learning process to just reiterate, to always just say it over and over till it just kind of sits and settles into the brain. The hypothesis test results, the p-value, the t-statistic, will similarly indicate that we must tentatively accept the null hypothesis, okay? And when it doesn't contain 0, then we can reject the null hypothesis, as I've stated. Okay, so we can see examples here. We can see the t-value for gender at 6.788. That is not in the no-fly zone. We've got a p-value, so because it's not in the no-fly zone, we fly all we want and we reject the null hypothesis, okay? And we have a p-value of 0.000, so we definitely have a much less than 5% error, which also tells us we can reject the null hypothesis. And then we've got a confidence interval that doesn't contain 0, so yet again we reject the null hypothesis. Let's find one that contains 0. All right, let's see, which one would you accept? Which one would you have to tentatively accept? So the first one that I see is the black variable. There's another. If you look right below it, the Indian variable, or Native American to be politically correct, I think. And so we can see the t-value of negative 0.277 definitely in the no-fly zone, as well as the negative 1.1 definitely in the no-fly zone. So we have to tentatively accept it. We lost the game. We accept the null. And we can see with the p-value at 78% error, not good. 24% error, also not good. And then we can see with the confidence interval the range that it would fall within. And it's not really very helpful because it's telling us, hey, it could be a negative relationship. It could also be a positive relationship. Or it could be no relationship at all because it falls within 0. Okay? So we have to tentatively accept that there is no relationship between, or no difference in salary between black and, what's missing? Hispanic. So between black and Hispanics, and between Native Americans and Hispanics. All right. All right, so the results of the confidence intervals and hypotheses tests are consistent. I will leave it at that. Okay? So, last lecture. Thank you all for listening. Thank you all for your patience this semester. And I really hope that you felt like you really learned, because statistics is a very powerful tool. And all it requires is a little bit of understanding, and you gain a whole lot of power in terms of understanding information that's being thrown your way, or creating knowledge, right? Going out, doing the data analysis, and sharing information. All right, well, get to it with your last practice exercise, and I'll see you on the flip side. Bye.